Everyone, my name is Sara El-Shawa. I'll be talking about one of the projects I've worked on during the summer as an applied machine learning intern. I'll introduce the topic and then talk about some of the stuff that I did, then pass it on to the rest of the PETS team, Privacy Enhancing Technologies team. So suppose there is a hospital in Ontario with data about a certain disease. Typically, data analysts can apply various conventional statistical models to this data to understand and interpret the information. But when you start thinking about using machine learning methods or deep learning methods specifically, there's not much that you can do without getting access to more data. So for example, if you want to train an AI-based tumor detector, it will require a large database encompassing the full spectrum of possible anatomies, pathologies, and input data types. So we need access to more data. Thankfully, there are other hospitals in Ontario, and actually this need for large databases for AI training has spawned many initiatives seeking to pull data from multiple institutions. This is sometimes called data lakes. But firstly, data like this is hard to obtain because health data is highly sensitive and its usage is tightly regulated. And then as soon as we centralize data, we run into many issues like regulatory, ethical, and legal challenges related to privacy and data protection, and also technical issues. So anonymizing, controlling access, and safely transferring healthcare data is not trivial, and sometimes it's impossible to do. And anonymized data can appear to be GDPR compliant, but then just a few data elements may allow for patient re-identification. So we can't really rule out patient re-identification or information leakage. Another reason why data sharing is not systematic, specifically in healthcare, is that collecting, curating, and maintaining a high quality data set takes considerable time, effort, and expense. And then this leads to these data sets having significant business value. So it's making it less likely that people will want to share this freely. So using machine learning or deep learning specifically, we want to develop a predictive model and we want to take advantage of the fact that we have data available in some sense from multiple sites, but we still want to take into account these issues. And this is where the privacy enhancing technologies come in. So it's crucial to ensure that an organization's clients and clients' data remain private and secure. And some of the recent PETs that have emerged include federated learning, secure multi-party computation, differential privacy, and homomorphic encryption. So kind of each person on this team focused on a specific PET, and I focused on federated learning, which I'll be talking about in the next few slides. But I do want to point out that it has been shown that when using federated learning alone, models can, under certain conditions, memorize information. So mechanisms like differential privacy or learning from encrypted data have been proposed to further enhance privacy in a federated learning setting. So ideally, you would want to use different types of PETs and frameworks at the same time to have like the maximum benefit. So diving into federated learning, it is a machine learning setting where devices collaboratively learn a shared prediction model while keeping all the training data decentralized. So here, each client's raw data is stored locally and it's not exchanged or transferred. And the two main ways of data partitioning when it comes to federated learning is horizontal and vertical. So the example that I gave you at the beginning of this talk with the multiple hospitals is an example of horizontal federated learning. So here you have two providers of the same service in different regions. So their user groups don't overlap, but because their businesses are very similar, the user features of the records are the same. So here you can see client A and client B, they have different users, which are the rows, but then the features are more or less the same. So with horizontal federated learning, you're increasing the user sample size, which will improve the accuracy of the model, all without compromising privacy. The other type of data partitioning is vertical federated learning, and this is available in the case that the user features of the two data sets overlap little, but then the users overlap a lot. So an example is you have two different institutions. One is a bank in one place, and the other is an e-commerce company in that same place. And because the user groups are likely to include residents of the area, there's a great intersection of the users, but then obviously they don't store the same kind of information. So banks record users' income and credit ratings, and then the e-commerce company would store some things like the browsing and purchasing history. So there's no intersection in the user features. But then using federated learning, we can infer user purchasing power by the bank saving and the preference by trading records from retail. And Ryan will be going through the work he's done on vertical federated learning after my presentation, and I'll focus on horizontal federated learning. So here's how it works. Your device, here being a hospital, will download the current model, and it improves it by learning from the data from that hospital, then summarizes the changes as a small focused update. And then only this update to the model is sent to the cloud using encrypted communication, where it's immediately averaged with other user updates to improve the shared model. So all the training data remains in the hospital, and there's no individual updates that are stored in the cloud. So these 3 steps keep repeating. Basically, each step is called round. And I know actually all of the examples that I've talked about include hospitals, and I think that's just because I'm mostly interested in healthcare data, but obviously there's many applications for federated learning. One of the more famous ones is Google's mobile keyword prediction, but also in like the financial sector, the autonomous vehicles, there's just a lot of different applications for federated learning. So some of the costs and benefits, it does require model sharing, which might not be possible in some cases. And then the actual cost is higher than processing information centrally, specifically at the beginning of setting it up. As for benefits, having personal data remain local is a strong security benefit. Federated learning makes real-time prediction possible since the prediction happens on the device itself. So it reduces the time lag that occurs due to transmitting raw data back to the central server and then shipping the results back to the device. And it's also compliant with data protection regulations like GDPR. So it allows for smarter models, lower latency, less power consumption, all while ensuring privacy. So diving into some of the tools, so the team has looked at the very beginning of our internships, we all looked into PySift by OpenMind, and PySift is primarily used for simulations that run homogeneous clients on a single large machine. What I think our conclusion is that it still is in its very early stages. We ran into many technical problems and opened some issues on GitHub. The repo is like updating every few weeks. So I suppose in the next coming months or so, we'd have like better results working with it. But I focused on TensorFlow Federated because that was just more well documented. And I'll talk about TensorFlow Federated in the next few slides. For resources, I just put 2 here. There's Leaf, which is a benchmark for federated settings. There's also FedML, which is a federated learning research library. So diving into the pipeline, so as I said, the framework that I used was TensorFlow Federated. It is an open source framework that's used to simulate federated learning. And currently the only 2 tutorials / data sets that are available by TensorFlow Federated are for image classification and text generation. So what I wanted to do is basically have this pipeline of using tabular data sets to make them into a federated, using federated learning on tabular data sets. So starting off with just any simple tabular data, making them into a federated data set, and then simulating federated learning on that. So the data set that I used was from Gemini. For those of you who don't know, Gemini is this huge database. I think has over 20 hospitals in Ontario now with over 200,000 patients. I took 4 Ontario hospitals from the data set, around 1,100 patients in total, and then features about the patients like age, sex, etc. And then for the model that I did, I used a simple MLP model using Keras, and I did a binary classification on if the patient had delirium or not, so just plain 1s and 0s. I did want to point out that my focus in this internship wasn't at the data set or the model. So it's more of putting together this pipeline, and I'm just using this data set and model to show you how it works. But I kind of set up the pipeline in a way where users can input any data set that they want, as long as it's tabular, with any model that they want to simulate federated learning. And then another point is, due to the sensitivity of healthcare data, I won't unfortunately be able to show you any results or plots or code, but I will explain the scenarios that I worked on, and I'm happy to answer any questions. So the first scenario, think of this as the most traditional kind of scenario. You only have one specific site, and you're only using the data from that site to train your model and test the model as well. So using the 4 hospitals, for each one, the training and testing for hospital 1 to 4, and you can see that the performance is dependent on the hospital. So hospitals 2 and 3 do actually a pretty good job with this very simple model, versus hospital 1 doesn't do that well. And then for scenario 2, I wanted to kind of simulate of like a centralized data set. So what I did is I'm training on 3 hospitals now, and I'm testing on 1 hospital's data. But here, this scenario does not have any privacy. So I had all of the 3 hospitals' data in one location, and then I'm testing on the 4th hospital. And then you can see that the test accuracy is on average higher than scenario number 1, which makes sense because we're increasing the sample size. But then with this scenario, it's not private. So scenario number 3 is me looking into just like scenario number 2, so training on 3 hospitals and testing on 1, but using federated learning and specifically using TensorFlow federated. So with that, we have a test accuracy of around 70%, which is, I guess, okay. Again, the data set and the model aren't the point of what I was working on during this internship, but it's more of this pipeline of doing these 3 different scenarios on any tabular data set. So in summary, all machine learning methods benefit from the ability to access data that represent real-world data, and federated learning is a promising approach to obtain accurate, safe, robust, unbiased models. And we now have a way to kind of compare the effectiveness and have these 3 different scenarios of using any type of tabular data set with any model that you want to simulate federated learning versus non-federated learning settings. And with that, I'd like to thank you all, and I'm happy to take any questions.